Hello everyone, welcome back to another lecture of solitons. Let's first recap what we saw last time. So we were looking at relativistic field equations in 2 dimensions for field u, a function of 2 coordinates, t for time and x for space, which satisfy this equation of motion here. And our aim is to derive conservation laws for such relativistic field equations. So the first thing that we did was to switch to light cone coordinates x plus or minus, defined like so, which allowed us to write partial derivatives in this way. And so, in particular, the equation of motion takes this very simple form, u plus minus, which is a second partial derivative of u with respect to x plus and x minus, is equal to minus the first derivative of the scalar potential v, which is a function of u. And then we define the notion of Lorentz spin, which is the number of x plus derivatives minus the number of x minus derivatives, which appears in any expressions that we'll look at. And this is useful to use the full power of special relativity, and in particular to organize our analysis of conservation laws. Then we saw that if we can find a pair of densities t and x of spins respectively equal to s plus or minus 1, such that they obey 2 conditions. So the first condition is essentially the continuity equation written in light cone coordinates, and it says that the x minus derivative of t is the same as the x plus derivative of x. That's the first condition. And the second condition is the limiting condition on the current, which in this case becomes t plus x must have the same limits, the same finite limits at plus and minus infinity. So if these 2 conditions hold, then the charge q defined as the integral over space x of t minus x turns out to be a conserved charge. And in fact, it's a conserved charge of spin s. So that's what we're after, a pair of densities t and x of appropriate spins which satisfy these 2 conditions. And we also observe that if we shift the densities t and x by a total x plus and x minus derivatives of the same function u of a fixed spin s, then so long as this function has, again, finite and equal limits at plus and minus infinity, again, this conserved charge is unaffected. So we'll always drop terms which are total derivatives of functions which have the same limits at plus and minus infinity for the purpose of finding the conserved charge. To make our life easier, we decided to look for so-called polynomially conserved densities, and we'll try to construct them spin by spin. So I remind you that a polynomially conserved density means that the density t of spin s plus 1 is a polynomial in x plus derivatives of u only, and each term must have exactly s plus 1 x plus derivatives in order for the spin of t to be equal to s plus 1. Following this general strategy, we managed by the end of last lecture to construct conserved charges of spin 0 and 1. So for spin 0, we saw that t was equal to u plus and x was equal to u minus, and that allowed us to construct the charge q0, which turned out to be a total derivative with respect to x, and therefore that was proportional to the difference of the values of the limiting values of u at plus and minus infinity. And this up to normalization is nothing but the topological charge that we have already encountered. For spin 1, it turned out that t had to be proportional to u plus squared. There was also potentially a u plus plus term, but that was a total derivative, and so we could drop it with no loss of generality. Then we found the corresponding x naught, and the conserved charge of spin 1 q1 became an integral over space of u plus squared plus 2 times the scalar potential B of U. We'll continue from here, and I will now go to full screen. This is where we are again. 4.16 is Q1, the conserved charge of spin 1. Before we proceed, let's make an important remark. Given a pair of densities, T s plus 1, x s minus 1, leading to a conserved charge Qs of spin s, we can switch the role of the two light cone coordinates x plus and x minus to find a new pair of densities with opposite spins, minus s minus 1 and minus s plus 1, which leads to a conserved charge Q minus s of opposite spin. So that's now the integral over x of t minus s minus 1 minus x of minus s plus 1. In particular, we had our charge Q1 above, which I write again is integral over x of u plus square plus 2 v of u minus 2 plus infinity. Then this remark tells us that we also have an associated charge of spin minus 1, which is given by an integral over x of u minus square plus twice the scalar potential v of u. Now we can take sum and difference with suitable normalization. So let's start from a sum q1 plus q minus 1, and will be convenient to divide this by 4. That's equal to integral over space of 1/4 u plus square plus u minus squared plus v of u, which we can rewrite in terms of time and space derivatives using the formula that we derived last time as 1/2 ut squared plus 1/2 ux squared plus v of u. So I remind you that the plus derivative is equal to the time derivative plus the space derivative, and the minus derivative is equal to the time derivative minus the space derivative. So the cross terms cancel out, and we just get the square of ut and the square of ux. But this expression is something that we have encountered already, and this is nothing but the energy. So the sum of the conserved charges of spin plus and minus 1 is simply the energy. That was the sum. Now let's look at the difference, 1/4 q minus 1 minus q1. So taking the difference, the dependence on the scalar potential drops out, and we simply get integral over space of 1/4 u minus squared minus u plus squared. And when we write this in terms of time and space derivatives, now the squares cancel out and the cross terms remain. And what we get is minus integral over space of ut ux. And it turns out that this is nothing but momentum. So from the difference of the conserved charges of spin 1 and -1, we get a new conserved quantity, which is interpreted as the momentum of the field. So both energy and momentum are conserved. Next, we try to construct a polynomially conserved charge of spin 2. So we start from a density T of spin 3, which is polynomially conserved, hopefully. So we'll only depend on x plus derivatives of u. And so in particular, this can contain 3 terms, or in general would be the linear combination of 3 terms, u plus plus plus, u plus plus times u plus, and u plus cube, corresponding to the 3 partitions of 3, into 3, 2 plus 1, and 1 plus 1 plus 1. At this point, we can observe that the third derivative of u with respect to x plus is a total x derivative. So this is u plus plus differentiated with respect to x plus. And similarly, the second option is also total derivative. U plus plus u, times u plus is the x plus derivative of 1/2 u plus squared. And since these are total derivatives of terms which vanish at infinity, because all the derivatives of u have to vanish at infinity by the boundary conditions, we will be able to disregard those 2 terms, plus u plus plus, and to 0 at special infinity. And therefore, such terms would not contribute to the conserved charge. Well, hence, we can take density T3 to be equal to u plus cubed, the only term which is not a total derivative without loss of generality. And now we compute the x minus derivative of T3 to see if we can find the continuity equation. We get the 3u plus squared times u plus minus, and next we use the equation of motion to relate u plus minus to minus v prime of u. So we get minus 3u plus squared v prime of u. And here comes an important point. I claim the right-hand side cannot be a total x plus derivative. And the reason is that the highest x plus derivative which appears, which in this case is u plus, does not appear linearly. In this case, it appears quadratically. So why do I say this, that the right-hand side cannot be a total x plus derivative? Because the highest derivative of u appearing, which is u plus, appears quadratically rather than linearly. Well, let's say that x, the second density, which would appear on the right-hand side of the continuity equation with an x minus derivative in front, is a function of u plus, u plus plus, etc., with the highest derivative term, which say has n x plus derivatives. Then, by the chain rule, the x plus derivative of x will be equal to the sum of partial derivatives of f with respect to its arguments, u with, say, I derivatives. So here I comes from 1, rather from 0, sorry, to n, times the x plus derivative of the variable that we just consider, u plus with the I x plus derivatives. And so this is a sum I from 0 to n, partial of f with respect to u I derivatives, and then we have u with one more derivatives, in this case I plus 1. Now, the partial derivative of f with respect to the ith x plus derivative of u is again just a function of u plus up to u with n derivatives, and I'll call the function gi, and that multiplies u with the I plus 1 derivatives. Now the highest derivative of x plus, which appears here, is u plus with the n plus 1 derivatives, and that comes from the term in this sum with I equal to n. So we'll have u plus with now n plus 1 derivatives, and that multiplies a function gn, which contains lower derivatives of u. Derivatives with at most n derivatives of u. And so that tells us that the term with the highest x plus derivative only appears linearly. So that's a necessary condition for the right-hand side of the continuity equation to make sense. The highest x plus derivative of u must appear linearly. But now in the case of spin 2, we just found the highest x plus derivative u plus appearing quadratically. And that means that there is no polynomially conserved charge of spin 2. This might be disappointing, but let's not give up. Let's try spin 3 before we despair. At spin 3, we need the polynomial density T4 of spin 4. And that can contain 4 terms from the 5 partitions of 4. One is the option we have 4 x plus derivatives of u, or we could have 3 plus 1, so u plus 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 times u plus, or we could have 2 plus 2, or we could have 2 plus 1 plus 1, u plus squared, or finally we could have 1 plus 1 plus 1 plus 1, which is u plus to the 4th power. Now again, the first term is the total x plus derivative of the third derivative of u. And the fourth term is also the total derivative of 1/3 u. Once again, we disregard these terms, since they are total x plus derivative of expressions which vanish at infinity. So we're left with the three options, but we can do better. So let's notice that furthermore, the second term u plus 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 times u plus can be written using the trick that we use when we integrate by parts as minus u plus plus squared plus a total derivative u plus times u plus. So because of this, we can disregard one of plus 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 times u plus and plus plus squared without loss of generality, because they differ by total derivative up to sign. So the most general expression for T4 up to a total x plus derivative is therefore a linear combination, say, of the third and the fifth term, or equivalently the second and the fifth term. We'll consider just the third and the fifth term. So I'll write T4 as u plus plus squared and linearly combined with u plus to the fourth squared. So it turns out that the coefficient of u plus plus square must be non-vanishing, so we'll normalize that to 1, and I'll normalize the coefficient of the second term as 1/4 lambda squared for reasons which will become clearer in the following. That's equation 4.19. So here lambda is a constant to be determined later. And 1/4 is for later convenience. Good. Now we can differentiate equation 4.19 with respect to x minus. And let's see if what we get is x plus derivative of a new density x2. So first of all, we get from the derivative of the first term, we get 2u plus plus times u plus plus minus. And from the second term, we get plus lambda square. The 4 cancels out from another 4 coming from the derivative. That was the reason for choosing a factor of 1/4 there, times u plus cube times the derivative of u plus with respect to x minus. So next we can use the equation of motion, which tells us that u plus minus is equal to minus v prime of u. So the first term becomes minus 2 u plus plus v prime of u derivative with respect to x plus, and the second term is minus lambda squared u plus cube v prime of u. Now we can rewrite the first term by computing the derivative with respect to x plus of v prime u. That gives us minus 2 u plus plus times v double prime of u times u plus. The second term will leave it. This result may not look very promising, but observe that the highest derivative of u appearing in the first term, which is u++, does appear linearly, and this in fact allows us to extract a total x plus derivative. So the first thing that we can do is to rewrite 2u++ u++ as a total derivative of u plus squared with respect to x plus. And then we use again the tricks that we are familiar with from integration by parts. We'll write this as the total x plus derivative of u plus square v double prime of u with respect to x plus, and then we subtract a term where we move the derivative from u plus square to v double prime of u. And when we do that, we get u plus cube v triple prime of u. So finally, we have the second term, which was minus lambda square u plus cube v prime of u. So now let me collect together the two terms that multiply u plus cube. So we have first the total derivative term minus u plus square v double prime of u plus u plus cube, which multiplies third derivative of the scalar potential minus lambda squared times the first derivative of the scalar potential. So now the first term in equation 4.20 is a total x plus derivative. That's good. That's what we're after. But in the second term, u plus, which is the highest derivative of u appearing in that term, does not appear linearly. So by the previous argument, the second term cannot be a total x plus derivative unless it vanishes. So the second term is a total x plus derivative if and only if the quantity in brackets vanishes. That's third derivative of the scalar potential minus lambda squared times the first derivative of the scalar potential. Now, if equation 4.21 holds, then the right-hand side of 4.20 is a total x plus derivative of x2, which therefore is equal to minus u plus squared times v prime of u, sorry, v double prime of u. And so we find the conserved quantity of spin 3, which is given by the integral over x from minus plus infinity of t4 minus x2 and t4 was u plus plus squared plus a quarter lambda square u plus to the fourth, whereas x2 is what we just found, so we get plus u plus squared times v double prime of u. So equation 4.22 is a conserved charge of spin 3. If and only if equation 4.21 holds. On the other hand, equation 4.21 does not hold, then there is no extra conserved charge of spin 3. Or at least there is no extra polynomially conserved charge of spin 3. That's what we have proven. To summarize, the theories which have an extra conserved charge of spin 3 in addition to the topological charge at spin 0, and the energy and momentum at spin plus and minus 1 are those whose scalar potential V of u satisfies equation 4.21, namely the third derivative of u minus lambda squared, the first derivative of u is equal to 0 for some value of the constant lambda. To conclude the lecture, let's analyze what happens when equation 4.21 holds for some value of the constant lambda, or rather lambda squared. So there will be essentially three options. Lambda squared vanishes, lambda squared is positive, and lambda squared is negative. Let's start with the lambda squared equal to 0. In that case, the third derivative of the scalar potential vanishes, so v is a quadratic function of u, which I can write as a plus b times u minus u naught squared, where a, b, and u naught are constants. And up to a linear redefinition of u, that leads to an equation of motion, which is the Klein-Gordon equation. And as I said in previous lectures, the Klein-Gordon equation is not particularly interesting from the point of view of solitons, because it's a linear equation. So in this case, you do get an extra conserved charge at spin 3, and in fact, even at higher spins, but that's essentially because the equation is linear. The next case is when lambda squared is not vanishing. we'll worry about the sign of lambda squared in a second. Now, in that case, we can think of equation 4.21 as a partial differential equation for b prime that we all know how to solve in terms of exponentials of plus or minus lambda u. And then we have to integrate once more to get the scalar potential. And the result is that the scalar potential is equal to a constant a plus a second constant b times exponential of lambda u plus a third constant c times exponential of minus lambda u. Now we need to consider a few possibilities. So first possibility is if only one of B and C is non-vanishing, then the equation of motion is either u plus minus equal to minus p lambda e to the lambda u. This would be the case if c is equal to 0, or u plus minus is equal to c times lambda e to the lambda u. That would be the case when b is equal to 0. And in either case, by a linear redefinition of u, we can rewrite the equation of motion in the following form: u plus minus is equal to exponential of u. This equation is known as the Liouville equation. The other possibility is that neither of B or C vanish. So if B times C is different from 0, then we have both the exponential terms. But again, by linear redefinition of u, we can write the equation of motion in the following form. And now we need to distinguish two cases. So in one case, lambda squared will be positive. In that case, we can write the equation of motion as u plus minus equal to minus hyperbolic sine of u. Please check this statement as an exercise. Whereas if lambda squared is negative, we can write the equation as u plus minus equal to minus trigonometric sine of u. So equations 4.24 and 4.25. So equation 4.25 is nothing but the sine-Gordon equation that we know and love. And for this reason, equation 4.24 is called the Sinch-Gordon equation. So to conclude, equations 4.23 to 4.25, so the Liouville equation, the Sinch-Gordon equation, and the sine-Gordon equation are special. They're special because they have hidden conservation laws that other generic relativistic field equations of the type u plus minus equal to minus v prime of u don't have. So only if the scalar potential takes a very special form, which solves equation 4.21 here, there exists a conserved quantity, a conserved charge at spin 3. So I should make a remark here that one could, in fact, carry on and find there are more and more hidden conservation laws. For the Liouville equation, the Sinch-Gordon equation, and the Sine-Gordon equation. But it turns out that there are more systematic ways to calculate and to find these extra conserved quantities. And you will study this in the second term. So I'll stop here for conservation laws of relativistic wave equations. And what we'll do next, starting next week, is to look at conservation laws for the KdV equation instead. Have a good weekend.